This is B. Naresh, working as assistant professor in ECE department. And today's topic is question bank discussion on FET amplifiers. That is module 5. So in this session, we are going to discuss how to write the questions from part A and part B. So let us consider the first question is from the part A. A UJT has the RBB is 10 ohms and RB2 is 3.5 kilo ohms, and find its intrinsic standoff ratio. So if you consider this unijunction transistor, we have the two bases, base 1, base 2 and emitter, and internally is a divider. Internally it can be converted into two resistors, equivalent resistance, RB1 and RB2 should be connected to ground, should be connected to the source. Now we need to find out this parameter, that is the intrinsic standoff ratio, and from that the intrinsic standoff ratio is defined as RB2 by RB1 plus RB2, and you can also write this, the total resistance means the summation of RB1 and RB2 is also represented as the total base to base resistance, hence it is represented as RB2 by RBB. So hence now we need to substitute the given specifications. So what are the specifications they given? RBB is 10 ohms and RB2 is 3.5 kilo ohms. So now we can substitute this is 3.5 into 10 power 3 divided by 10 ohms. Now I can observe this intrinsic standoff ratio. Now let us consider in the common drain amplifier, let the source resistance is 4 kilo ohms and the gate resistance is 10 mega ohms, and the mu means amplification factor is 50, internal drain resistance is 35 kilo ohms. Evaluate the voltage gain and input impedance as well as the output impedance. So this is the given a circuit for satisfaction of common drain amplifier. So means that for a common drain amplifier, we know that output is taken from the source and input is passing through the gate terminal, and based on that the given specifications are the source resistance means this RS value is 4 kilo ohms and the gate resistance is 10 mega ohms. And generally we know that from the JFET configuration, to control the flow of drain current, the gate resistance should be very large, means the FET contains high input impedance, hence the input impedance RG is represented as 10 mega ohms. Then internal drain resistance, it is also called as the AC resistance, that is they represented as 35 kilo ohms. Now we need to evaluate for this question voltage gain, input impedance ZI, you can also write RI, and output impedance as a Z naught array R. To solve these parameters, so if you recall the voltage gain of common drain, before that we know that generally any voltage gain is defined as it is a ratio of output voltage to the input voltage V0 by Va. So from that, from the common drain amplifier, it is represented as mu times of Rs by 1 plus mu times of Rs plus Rd. Means you can substitute the given specifications. The mu value is a 50 and Rs value is a 4 kilo ohms, means 4 into 10 power 3 divided by 1 plus mu times of Rs means 50 plus 1 into RS, that is 4 into 10 power 3 plus, and the small RD means 35 kilo ohms. Now I can solve this one. It gives that the voltage gain is 0.36. So hence we observe the voltage gain is 0.36 for a given specifications. Now similarly, now we need to calculate the input impedance. So if you observe this given circuit, from the given circuit, now we need to calculate the input impedance, that is Zi. So Zi is represented as, so here this input impedance is proportional to this, the given circuit resistance, that is gate resistance RG. Hence, here we consider as the input impedance that is equal to RG. So from the given specifications, we know that the Zi, that is RG, is equal to 10 mega ohms. Now similar to that, we should calculate output impedance. So here the output impedance is represented as the output side, if you observe the output side, and that is the parallel combination of the means the reciprocal of the transconductance, and with RS, output resistance, that is RS. But here, if you observe this mathematical relation, here the known parameter is RS is a known parameter, and but we need to first calculate the GM. To understand this one, so from the characteristics of the FET, we have the one relation, that is mu is equal to GM times of small rd. And if you observe this relation, the known parameters are mu and rd is there, the unknown parameter is gm. So hence we should calculate this gm. Gm is equal to mu by rd. So where mu is a 50, small rd is 35 kilo ohms. So hence 35 into 10 power 3. Then it gives the transconductance. So hence the Z0 is 1 by. So this is Gm value is 50 by 35 into 10 power 3 is parallel combination with Rs, that is 4 into 10 power 3. So if you solve this one, then it gives that 595.7 ohms. So this is the parallel combination for output impedance. So hence we substitute the given specification values in this relation. Then we observe this output impedance is 595.7 ohms. Now see another question. In the common source amplifier as shown in below figure, let the capital RD means external drain resistance is 5 kilo ohms and the gate resistance is 10 mega ohms, amplification factor is 50 and internal drain resistance is 35 kilo ohms. Evaluate the voltage gain, input impedance and output impedance Z0. The given circuit acts as a common source amplifier. So hence, because the source is connected the common for input side as well as the output side, and the output is taken from the drain terminal, and external drain biasing resistance is 5 kilo ohms and the gate resistance is 10 mega ohms, and this amplification factor is 50 and internal drain resistance this contains 35 kilo ohms, means 35k. Then we need to calculate the voltage gain, input impedance and output impedance. To observe this one, so first we need to identify the what is the voltage gain here. Then you can refer this amplifier analysis, common source amplifier analysis. So in that session, we discussed the mathematical relation of the voltage gain of the common source amplifier by using the small signal model analysis. So from that, so here I taken as this is the voltage gain is represented as minus mu times of capital RD by small rd plus capital RD. So means this is minus and the mu is a 50 and the capital RD is a 5 kilo ohms means 5 into 10 power 3 divided by the small RD is 35 kilo ohms. So means 35 into 10 power 3 plus capital RD value is 5 kilo ohms. So mean this is 250 into 10 power 3 by 40 kilo ohms. This K the cancel. So means approximately this voltage gain gives the minus 6.25, where this negative sign indicates a 180 degrees phase shift with respect to the input signal. Means the output signal is 180 degrees phase shift with related to the input signal. It's not a negative magnitude that indicates a sign of the means the polarity of the output representation. Now we need to calculate the input impedance, that is Zi is again equal to RG. So from this the Zi value is directly represented as 10 mega ohms. So why? Because of that in the given specifications RG values are represented as means the gate resistance is represented as 10 mega ohms. Then we need to calculate the output impedance. So means if you observe the circuit at the output side from the small signal model, we know this mathematical relation. ID is equal to Gm into VGS plus 1 by RD into VDS. So let us take this is the drain current is flowing and this one current source, that is Gm into VGS plus 1 by RT into VDS, and this is a VDS, and here we are going to verify the output voltage. Let us take this is the source and this terminal is the drain terminal, and from the this is small signal model, and from the circuit configuration externally it is connected a load resistance or external drain resistance, that is R. So now we are going to observe this output impedance Z0. So hence the Z0 is the parallel combination of external drain resistance and internal drain resistance. So where you can substitute this parallel combination means RD into small rd by capital RD plus small rd. Then you can substitute these resistances. So this is 5 kilo ohms and small rd is 35 kilo ohms. So once again the capital RD is 5 kilo ohms plus 35 kilo ohms. Now it gives that the Z0 value is 500 ohms. So that is approximately equal to 500 ohms. But otherwise, you can also take, suppose if the two resistances are unequal and those two resistances are in the parallel combination, and it gives that the equivalent parallel combination is that is equal to smaller resistance value. So from that, otherwise you can write that Z0 is directly proportional to RT. So means the RT value is 5 kilo ohms. We'll see another problem in the common gate amplifier. Let capital RT is a 2 kilo ohms, RS is 1 kilo ohm, transconductance Gm value is 1.43 into 10 to the power of minus 3 mho mhos, and small RD is 35 kilo ohms. So now we need to evaluate the voltage gain, input impedance, and output impedance, that is data. So now, based on these given specifications, and the given specifications are related to common gate amplifier. So hence we need to solve the voltage gain and input impedance as well as output impedance based on the common gate amplifier. So let us assume the given specifications, and from the problem statement, the given specifications are the external drain resistance is 2 kilo ohms, and the source resistance is 1 kilo ohm, and the transconductance is 1.43 into 10 to the power of minus 3 ohm inverse or ohms, and internal small drain resistance, that is 35 kilo ohms. Now we need to evaluate the voltage gain, input impedance, and output impedance. Hence, so from the common gate amplifier analysis, otherwise you can refer the CG amplifier analysis video session. And from that, so here I am recalling the mathematical relations of voltage gain. So that voltage gain is represented as Gm times of RT plus 1 times of capital RD by capital RD plus small r. Now you can substitute the given specifications. So means Gm value is 1.43 into 10 to the power of minus 3, and the small rd is 35 kilo ohms, 35 into 10 power 3 plus 1 times the your external drain resistance, that is 2 kilo ohms, 2 into 10 power 3 divided by, and the capital RD value is 2 kilo ohms, hence 2 into 10 power 3 plus small RD is 35 kilo ohms, hence 35 into 10 power 3. You can solve this ratio, so it gives that the voltage gain is 2.75. Now we need to calculate the input impedance for the common gate amplifier. So from the common gate amplifier configuration, and we know that the input impedance is the parallel combination with the source resistance and the reciprocal of the transconductance. So here, then they are given directly the transconductance. We know this transconductance value, hence this RS value is parallel with the reciprocal of the transconductance. Hence, RS is a 1 kilo, 1 into 10 power 3 is parallel with the transconductance, that is 1 by Gm, means 1 by 1.43 into 10 to the power of minus 3. So hence means 1 into 10 power 3, 1 by 1.43 into 10 to the power of minus 3 by 1 into 10 power 3 plus 1 by 1.43 into 10 to the power of minus 3. You can simplify this one. It shows that the Zeta is 0.41 kilo ohms. So similar to that, we need to calculate the output impedance Z0. The Z0 is proportional to the external drain resistance, that is capital RD. So hence from the given specifications, the Z0, that is equal to RD, that is nothing but a 2 kilo ohms. Now coming to another question, illustrate the construction details of Ujt and explain its operation with the help of equivalent circuits. So for this case, first you explain how the Ujt is constructed, means that, so let us take, this is a piece of semiconductor material, and let's take this is the N-type a semiconductor bar. So one end it is connected to terminal base 1, one end is connected to base 2, and opposite side a heavily doped material is connected, that is called as a p-type material. Then it forms the one junction, and this is represented as emitter. So from this, and the symbolic representation of UJT is, so here this is emitter, base 1 and base 2. Then if you want to explain the operation with the equal circuit, means this transistor is replaced with the internal structure is, it contains p-type and n-type. Then the internal, that is a channel, the channel is replaced with the equivalent resistances. It contains two resistances, RB1 and RB2. It is biased with a VBB. So it is biased with VBB. Then, so from this, now it should be connected to ground potential. Here we are going to apply a input voltage. Now first we need to identify at which voltage the UJT changes the state from on state to off state or off state to on state. To identify this one, first we need to find out how much equivalent voltage is produced at this node. So hence, now I'm going to find out this voltage across this. Let's take this is some node voltage. I take it as a VA. So if you want to apply the KVL principle of this node, you can write this one. So we can write this VA minus VBB by RB1 plus, again, from this node to ground potential, the potential difference is represented as VA minus 0 by across the resistance, that is RB2 equal to 0. By using this mathematical relation, we need to find out how much net voltage will be produced with respect to the biasing components and the DC sources. And if you simplify this one, then we can write this VA by RB1 plus VA by RB2, that is equal to VBB by RB1. And in this relation, if a VA is a common, then you can write this is 1 by RB1 plus 1 by RB2, that is equal to VBB by RB1. You can take the LCM, then it becomes, so VA times of, so if you take the LCM, RB1 RB2 means this is RB2 plus RB1 by RB1 RB2, that is equal to VBB by RB1. So this RB1 is a get cancel, hence from that the net voltage is represented as VBB, it's the RB2 by RB1 plus RB2. And this factor we can also replace with the intrinsic standoff ratio. So hence it is represented as eta. So hence the net voltage is represented as eta times of VBB. Now we need to, based on this, we should explain, these are the equivalent circuits. Now we can explain how this UJT changes from non-conducting state to conducting state, means. And if you recall the diode principle, we know that, and based on the semiconductor diode, your anode voltage must be greater than of the cathode voltage, then only the diode enters into the conducting state. If you apply this principle here to identify the operation of the unijunction transistor, so means that your applied input voltage must be greater than of eta times of VBB, then only the UJT enters into conducting state. That conducting state is called as on state. Else, otherwise means your applied input voltage is less than of eta times of VBB. The UJT is a non-conducting state, hence the state is represented as off state. Then based on this, you should draw the equivalent circuits. Now the next question is, explain the tunneling phenomena of a tunnel diode with the help of necessary energy band diagram. So actually, for this question, you should write first what is a tunneling diode, and then write what is the difference between an ordinary diode and a tunnel diode. So here, actually, the tunnel diode is made up with a heavily doped materials compared with a normal semiconductor diode or P-type and N-type material. So based on the Fermi levels or energy levels will be different. So hence, you should draw the energy band diagram here, and what is the position of the valency band, and what is the position of conduction band, and what is the level of Fermi level. Then apart from that, you can apply some biasing voltage for the tunneling diode. Then how this Fermi level means how this valence band and the conduction band levels are changes due to that, how this tunneling phenomenon is occurs means it looks like, so the majority of the charge carriers are flowing from the one region to the another region to allow the maximum conduction. Means you should explain at which voltage and based on the doping levels, it allows the maximum flow of conduction across the tunnel diode. So for this case, you should refer this video link. So in this link, we observed the tunnel diode principle and construction and operation with energy band diagrams. Now, illustrate static and firing characteristics of SCR and explain the shape of the curve. So for this case, we should identify the static characteristics means of firing can be. So generally, this SCR is made up with a 4-layer. So that is represented as P, N, and P and N. So means this is P1, N1, P2, and N2. It contains the 3 junctions J1, J2, and J3. So this P1 side it is represented as anode, and the bottom of N2 is connected to cathode, and nearby this junction, so we are going to connect a terminal. The terminal is called as a gate. Now, so then you can explain how to, then you can apply the biasing voltages. Initially, let us take the gate voltage is 0, means the input biasing voltage is applied between gate and the cathode, as well as another biasing voltage is required anode and cathode. So then we'll see how you observe means you should explain what happens when the gate voltage is 0, then what happens your anode voltage is increases between the 3 junctions or the 3 layers. Then draw the characteristics, then how the curve should be like it. And then what happens even if you apply some gate voltage in a positive direction or negative direction, then you should explain with the characteristics how this SCR will be changes from a on state to off state or a half state to on state. Then explain the VI characteristics of xenon diode and distinguish between avalanche and Xenon breakdowns. So for this case, first you draw the xenon diode, then you can explain how the xenon diode is constructed. Then what is the advantage of this xenon diode, why we go for the xenon diode. Then apply the biasing voltages, means again you can apply the forward bias and the reverse bias. Then you should explain what happens when the forward bias is applied to the xenon diode with respect to the characteristics in terms of voltage and current. And similarly, you should write means you should explain what happens. A reverse voltage is passing through the xenon diode with a characteristic, that is Vi characteristics. So then we should explain what are the differences between avalanche and xenon breakdown. So here we should explain what is avalanche breakdown mechanism, and what is the xenon breakdown mechanism, and how to differentiate this annular avalanche and xenon. So if you want, you can refer this xenon diode characteristics video session. Then outline the small signal model of common gate FET amplifier. Derive the expression for voltage gain and output resistance. So for this case, first you should know the generalized small signal model for FET amplifier. So from the FET configured characteristics and operation, we observe that the drain current is a functioning of VDS and VGS. Based on that, we identified, so ID is represented as GM times of VGS plus 1 by RD times of VDS. And if you draw this a small signal model for JFET and generalize it on this one, this is gate, and output side taken the drain, common terminal connected with source. So this is generally it is represented as VGS, and here we are passing the input signal Vi. Now we need to represent this mathematical relation. This is GM times of VGS plus 1 by RD times of VDS. Then here we are going to observe the output voltage, and here the current is the flows value. So gate and the drain and the source. Okay, by using this, the generalized small signal model for FET amplifier, now you should redraw into the common gate configuration. Means, what is the common gate configuration? Means gate is a common for input side and output. Means source is taken as input terminal and drain is taken as the output. Means you should draw like that. This should be redraw in terms of common gate amplifier. Then identify apply the KVL analysis. Then to identify these voltage expressions for mathematical relations for voltage gain and output resistance. Then if you want analytical, you can refer that common gate FET amplifier using the small signal analysis video link. Now similar to that, outline the small signal equivalent circuit of FET amplifier in a common source connection and derive the expression for voltage gain, input impedance, and output impedance. So if you want to attend this question, then you can also first you can draw the small signal model of JFET amplifier under this common source connection. Then that should be converted into your external diagram. Means you should place your external biasing resistance like input resistance RG and output resistance is RD. Then apply the KVL. Then identify the mathematical relation. Means you install the mathematical relations for voltage gain with input impedance as well as the output impedance. So if you want, you can refer this link. So in this link, we observed that the analysis of common source amplifier by using the small signal model. And demonstrate the operation of UJT and sketch its characteristics. So for this case, just now we discussed that how we can explain that. Means we observe this internal structure, and internal it contains RB1. This is RB2. It should be connected to ground. It is connected to biasing only VBB. And we identified here it contains a eta times of VBB, where eta is represented as intrinsic standoff ratio, that is represented as RB2 by RB1 plus RB2. Hence, this eta is represented as RB2 by the total bias resistance, that is RB. Now here we need to pass input voltage. Now, then you should explain this construction, and then you can explain the operation of this UJT. Then, so here for this UJT, x-axis is represented as I, and the y-axis is represented as V. Now you can observe what happens. Now we know that when if a VI is less than of eta times of VBB, then the UJT is acts as a non-conducting state. The UJT state is represented as non-conducting state. Hence, the state is represented as off state. So we know that if based on the principles of a normal semiconductor diode, if you recall that semiconductor diode principle, if the diode is reverse bias and it acts as off state, under this point the output voltage is proportional to V applied input voltage. So here also the voltage drop across this PN junction or emitter side, that is equal to your applied input voltage means. So but current is a 0, but output voltage that is equal to your applied voltage. So here I taken this point. Then what happens, we'll see if VI is just greater than of eta times of VBB. Now the diode is, so let's say this is the PN junction. This PN junction is acts as a conducting state. So hence D is on means UJT is also enters into the on state. If the UJT is on state, what happens? The current rate is increases and the voltage across this UJT becomes to your a minimum. Maybe that we know that when the diode is according to diode principle. So if the diode is under forward bias, then it is replaced with a short circuit. The voltage drop across the short circuit path is represented as 0. So hence from this output voltage is reaches to value. It means when the current is increases, it should be reaches to some voltage, minimum voltage. This voltage here it is called as a value voltage, and at this point when the UJT changes the state from off state to on state, how much voltage is required, that is called as the peak voltage. Then it is from again status with a normal characteristic. So then this is the characteristics or emitter characteristics of N junction transistor. Hence it is represented as VE. So hence it is represented as VE and IE. Now outline the VI characteristics of Xenon diode for forward bias and reverse bias voltages. So for this question, first you draw the circuits for Xenon diode under forward bias and reverse bias. Then draw the characteristics under the forward bias and your reverse bias. So here we know that Xenon diode. So this is under forward bias. It normally looks like PN junction diode characteristics, but it is specially designed for a reverse bias. Let's take this is VF and IF. So under the reverse bias also it allows the conduction. So after this is take the Xenon breakdown and some contains some avalanche breakdown. Then you can explain how this curve will be occurs. Similarly, explain the silicon control rectifier characteristics with a transistor equivalent model. So if you observe here, let us take the SCR internal structure is represented as P1 and N1, P2 and N2. So let us take this is J1, J2 and J3. This is anode and means I'm converting into this one. This is one PNP transistor and taken as NPN transistor. So means let's take this is P1, N1, P2. Another one I taken as this one. So means this is N1, P2 and this is N2. So these two interlink. these two entering, and here it is anode and this is cathode. So then we have this is one junction J1. So at this point N1 and the P2, this junction is J2 and this junction is J3. So hence we require, this is the PNP transistor. So if you take in this one PNP, so this is anode means P, N and P. So let us say this is a collector, base and emitter. Then similarly this is, so again we need to take this base is connected to, means this is NP, I mean this is base, this is collector and emitter. So this emitter is connected to cathode. So hence let us take, and this is emitter, collector and a base, PNP transistor. Similarly taken as NPN transistor, let us take this is PNP transistor, this is NPN, collector, emitter and a base. If you observe this one, for a PNP, base is connected to collector of this one, so hence it is connected to collector of this one. And similarly the emitter of PNP transistor is connected to base, so then it is connected to base. Now this is connected to anode, this is connected to cathode. The interconnection of nearby the J2, that is connected to gate terminal. So then after this you can explain the characteristics with this transistor. So means the characteristics are looks like normal silicon controlled rectifier. So if you want you can refer the SCR operation video session. So up to this point in this session we observed that the part A and the part B questions from the module 5, that is FET amplifiers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.